I now call to order the 2496th meeting and the 93rd Joseph Henry Lecture in what is now the 153rd year since the Society's founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein, for the few of you who don't know. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the 2024 Annual Joseph Henry Lecture by Brent Seales. The Society is grateful to PSW full year series sponsors, PSW member Mike Helton, and Helton Associates LLC for their crucial support. Please join me in thanking them. We are also grateful to the IP law firm Millamite, Solano, and Brannigan, me in particular, since I'm a partner there, but also PSW for Millamite's longtime support of the presidents and the Henry Lectures. Tonight is the 93rd Annual Joseph Henry Lecture, honoring PSW's founder, first and longest serving president, Joseph Henry. He served as president of the Society from its founding in 1871 until his untimely death 7 years later in 1878. He was the preeminent American physicist of that time, an American Rutherford. He was also perhaps the most prominent American scientist of that time. He's best known for his many contributions on the study of electricity and magnetism, and for his finding that a powerful magnetic field is induced by flowing current through an insulator conductor wound around a ferrite core. This work led to the development of very much stronger electromagnets, among other things. And his work on induction and inductance led directly to the invention of the telegraph, and later to the invention of the telephone. In fact, Henry developed early versions of the telegraph and consulted with Samuel B. Morse, who's more familiar to you, who ultimately invented the telegraph system that came to be widely adopted. Among his roles in founding and serving in many other institutions to foster science in America, Henry also was the founding secretary of the Smithsonian Institution. Henry's death was headline news, not only in America, but also around the world. And here in Washington, the city quite literally closed down to mourn his passing. We honor Henry today with this annual series of lectures on important topics of the day in science that would certainly have interested him. We also honor him today by using the Society's ceremonial gavel, which was carved from timbers of the White House, recovered from the White House during the Truman Reconstruction of 1949 to 1952. But the wood is much older. Apparently it was used in the White House Reconstruction of 1815 to 1817. Why did it have to be rebuilt then? Anybody know? Because our special friends, the British, burnt it to the ground. Yes. Anyway, we enjoy using it and bringing it out on this occasion to honor our founding president. So thank you, Joseph Henry. So I'm pleased to note the following new member, Brent Seales, our speaker tonight, who learned of PSW science, I think, from our invitation to him to speak here tonight, and whose interest will be clear in some small part, actually no small part, to you from tonight's lecture. If you're interested in membership, you You can access a membership application on the PSW website by clicking on the Join button that you'll find on the homepage in the upper right-hand corner. If you're here in the Powell Auditorium, there are cards in the back with QR codes on them that you can use that will take you directly to the website, to the membership application page. And I think one may even take you directly to the application page. So just pull out your credit card and fill out the application form, and we will be pleased to accept you to membership if genuine, bona fide interest in science. All members are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, and if you choose to wear the ribbon of the society, if you're a new member and you haven't received your signed copy of the bulletin, please come see me after the meeting. I know there are 2 people who want their bulletin, so don't forget to come and see me. There are also some people in the audience who have been accepted to membership, but I did not have a chance to get them into my announcement tonight because they came in later, close to when I was preparing these. So they will be announced next time. Fear not. Okay. Not a PSW member? Please join. Recording Secretary Scott Matthews will now present the minutes of the 2495th meeting and the lecture by David Spergel on lessons from the universe's baby picture. Scott, stage is yours.
Thank you, Larry. Good evening.
Pause.
On May 3rd, 2024, in the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2495th meeting of the Society to order at 8:03 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Richard Pyle titled Diving Deep into Biodiversity, Leveraging the Latest Technology to Explore Deep Coral Reefs. The minutes were accepted as read. President Milstein then introduced the speaker for the evening, David Spergel of the Simmons Foundation. His lecture was titled Lessons from the Universe's Baby Picture. The speaker began by stating that our universe is both remarkably simple and remarkably strange, and that the talk would emphasize what we have learned over the past 20 years from studying the cosmic microwave background, or CMB, the heat left over from the Big Bang. He said that 5 numbers determined all the large-scale properties of the observable universe: the age of the universe, the density of matter, the density of atoms, the density of dark matter, the, quote, lumpiness of the universe, and how the lumpiness varies with scale. Spergel then discussed the strangeness of the universe and the things we do not understand, including dark matter, dark energy, matter-antimatter asymmetry, how the universe began, and what drove early expansion. Based on the assumptions that the universe is uniform and isotropic, Spergel presented a quick history of the universe. It started out hot, dense, and filled with radiation. As it expanded, it cooled. In the first minutes, light nuclei formed. After 400,000 years, atoms formed. After 100 million years, stars began to form. After 1 billion years, galaxies formed. He said that looking at the cosmic microwave background, or CMB, is effectively looking at the universe when it was about 400,000 years old, as that was the point when the universe became transparent to electromagnetic radiation. This is the, quote, baby picture he refers to in the title of his talk. Spergel discussed the fact that measuring the statistical fluctuations of the CMB allows the determination of the 5 numbers that describe the universe. Additionally, fluctuations in the CMB provide a quantitative measure of the curvature of the universe, giving an indication of whether the universe will continue expanding, reach a maximum and remain static, or reverse course and collapse. He said that the current model of the universe, combined with the statistical observations of the CMB, indicate a universe that is 13.77 billion years old, 5% atoms, 25% matter, 70% dark energy, with scale invariant fluctuations. Spergel commented that while the quality of the data acquired from both satellites and ground-based telescopes has improved dramatically over the past 20 years, the model of the universe and the numeric parameters calculated from the data have changed very little. He concluded his talk by saying that cosmologists are historians looking back in time who have constructed a simple model of the universe that seems to fit all the observations, and that the model is based on aesthetic principles of mathematics, which seem to work remarkably well. The lecture was followed by a question and answer session. A member asked about the CPT theorem and whether symmetry principles would imply that the universe would contract. Spergel responded that the universe cannot be CPT symmetric due to both matter-antimatter asymmetry and the weak interaction, which has been demonstrated to be CP violating. A guest asked first about the units of lumpiness and second about the Hubble tension. Spergel said that lumpiness corresponds to fluctuations in temperature and that the amplitude of these fluctuations is on the order of 1 part in 10 to the 5. Spergel explains that the expansion of the universe, the rate of expansion of the universe, the Hubble constant, should have a value of about 68 based on CMB data. The Hubble constant can also be estimated from Cepheids, a type of pulsating star, which yields a value of about 72. The difference between these two numbers is the Hubble tension. Spergel said that if future measurements show these two values converging to a value of about 70, the Hubble tension disappears. Whereas if these two values are actually different, it indicates a problem with one of the models. A viewer on the live stream asked about gravitational waves and the insight they might provide on the early universe when combined with CMB data. Spergel commented that the upcoming LISA mission, Laser Interferometer Space Antenna, could potentially provide information about gravitational fluctuations in the early universe, and that the scale and amplitude of such fluctuations might complement the observation of fluctuations in the CMB. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers for upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,495th meeting of the Society at 8:35 p.m. Eastern Time. Temperature in Washington, D.C., 14.4 Celsius. Weather, mostly cloudy. Audience in the Powell Auditorium, 72. Viewers on the live stream, 22, for a total of 94 live viewers. Views of the video in the first 2 weeks, 717. Respectfully submitted, Scott Matthews, Recording Secretary.
We now turn to tonight's lecture by Brent Seales on Unlost, recovering the text of burnt and carbonized scrolls, reading Herculaneum papyri using X-ray CT and AI. Brett is the Stanley and Karen Pigman Chair of Heritage Science and Professor of Computer Science at the University of Kentucky. Brett is the founder of EduSlab. Is that correct? EduSlab, a heritage science research lab at the University of Kentucky for the development and application of techniques in machine learning and data science to the digital restoration of damaged materials. He is also a co-founder of the Vesuvius Challenge, an international contest formed around the goal of the virtual unwrapping of Herculaneum scrolls, about which I think you'll hear more later. He's currently working on the recovery of information from challengingly damaged ancient material, such as the Herculaneum scrolls and the Dead Sea Scrolls, and the effort has achieved notable successes in a number of cases, including texts from Leviticus, the Acts of the Apostles, Philodemus, and on Epicureanism. The recovery of readable text from these ancient scrolls is really an historic event. The first glimpse into the writings of foundational civilizations that these techniques are going to make accessible for the first time in thousands of years. Brent earned a BS in computer science at the University of Southwestern Louisiana and an MS and PhD in computer science at the University of Wisconsin-Madison. All questions will be fielded in the Q&A session after the lecture, as usual. Without further ado, Brent, the stage is yours.
Thank you. All right, well, just as it got raucous there with the minutes, you asked me to the stage, so this should be fun. Thank you so much, Larry, for inviting me for this very special lecture, the 93rd Joseph Henry Lecture. I didn't want to wait till it became a prime number, so I thought I would just go ahead and accept 93. And thank you, Robin, for all of your logistics. I appreciate it. And thank you, audience, for coming out tonight to listen to what I have to say about my project, which I have titled Unlost for tonight. I could say found. Lost and found we're familiar with. Unlost, I think you'll see the meaning as I go forward. I couldn't start into this work at all without acknowledging the many people who are working with me to be able to achieve the results I'll talk about tonight. So I just want to thank those people, starting with Stan and Karen Pigman on the first slide, who have endowed my position at the University of Kentucky. But I want to thank these undergraduates who this year spent time in the lab with me, and I'm sure they're watching tonight and will be critiquing my talk as I have critiqued them all semester long. So that should be interesting. I want to thank my staff at the University of Kentucky. This is my Kentucky team for their steadfast help and work in these projects. I also want to thank the academic researchers, specifically James, Stephen, and Anken, who are part of my team and are very advanced in their work. And finally, I want to acknowledge the Italian team who's been working with me in Naples, Italy, to do the work actually at the Biblioteca Nazionale di Napoli, where the Herculaneum material largely is stored. And I can tell you certainly that I am the most ugly person of all of these people in all of these photos. All right, I want to start my talk by noting the inspiration for how this work began. A little story that's really important to me, and then I'll talk about sort of origins so that we can set the stage for the breakthrough that we had with the scroll from En-Gedi and then Herculaneum. So inspiration. In the early 2000s, I was sent a letter from a woman by the name of Cheryl Sechrist, who lives in Maryland, and the letter looked like this. It was one page and it had faded, and she wanted to know if I could help restore it. And at the time, I was early in my career on doing digital restoration. And so we took this letter into the lab and we tried a few things that didn't work. And then eventually we realized that we could do a color transformation by taking the RGB space and converting it to what ended up being LAB space, basically doing a transformation to make the part of the color space that had the ink signal appear. And when it appeared, we were then able to see that the writing signal in fact was on the letter, and it gave us the foothold that we needed to do a complete restoration. And so what we were able to do with this letter is actually read that it was from her father. Dearest Cheryl Ann, hello, my little darling. How are you this evening? Fine, I hope. And you see in the upper right, USS LST 450, October 16th, 1944. This letter was from the Second World War, landing ship tank 450 in the Pacific Theater. Some called it large, slow target. Frank was on this ship and he was writing to his daughter, and his daughter was 8 months old. Honey, just think before long you will enjoy your first Christmas. I only wish I could be there to see you get your first Christmas gift. Be a good girl, oceans of love, your daddy Frank. XXX. Is that not sweet? Is that not a reason to try to pull text back from the brink? So what you're going to hear tonight is my quest to be able to recover text, stories, to be able to restore the sacred contract between an author and a reader, and in this case, the author is a father and his daughter. Okay, so for some origins, This work started in the British Library with the Cotton Collection, and in particular, Cotton Collection holds a manuscript called Beowulf. You may have heard of that. The Cotton Collection also has a number of other important manuscripts. We worked with a professor at the University of Kentucky early in the mid-1990s on the Beowulf manuscript, and in particular, the construction of what we called an electronic version, an electronic Beowulf. And you see here the glorious 1995 Mac interface version of what at the time we were trying to put together. 1995, if you know your history, there really wasn't an internet, so everything that we had captured from the manuscript was on a CD, and then the goal was to build software that could reference that CD and basically show these images, including some special images that were taken with ultraviolet light, for example, to show some things that weren't visible to the naked eye. And I took that work, which was a single project, and turned it into my first NSF grant in the digital library field. And some of you from NSF are here tonight. I just want to tell you how much I appreciated the Digital Library Initiative of the 1990s and my part in it, where you can see from this slide from a faculty seminar I gave in the year 2000, when society did not collapse, it turned out, but where I outlined that I was interested in new ways of digitizing things, ways of accessing that content that were distributed and extensible, and, jump the gun there, and new restoration techniques, including mosaicing and flattening and volume visualization. So let me show you what we were doing at the time. Here's a manuscript on the left called the Venetus A. It is the oldest complete copy of Homer's Iliad, and it's in the Marciana Library in Venice, Italy. And that manuscript is able to be opened and it's able to be photographed. On the right, you see another manuscript in the Cotton Collection that was not restored. It's basically under this bell jar, and it can't be opened because it's made of parchment. It was burned and then made wet with the water that put out the fire, and not restored so that we can see what the state was of some of those manuscripts that suffered that damage. What I became interested in through that work was a method that could approach some of the most badly damaged materials in libraries and museums across the world. What I was unaware of at that point is where that would take me, and where it took me was to a certain volcano called Vesuvius and a certain town called Herculaneum. So I'm going to back into this lecture by talking first about the materiality, and then we'll talk a little bit later about the contents of these very, very important scrolls. Herculaneum contains a cache of carbonized papyrus that runs the gamut in terms of its physical disposition. On the left, you see a scroll that was opened, and the sections are half a scroll wrap with the carbonized papyrus. And you see divisions because the scroll was probably cut on its side so that we could take, like an onion, the papyrus and then paste it down. On the right, when chunks fell out, they simply were put in a drawer because nothing could be done with them. And then there are actually scrolls that are completely intact. And these completely intact scrolls represent a very enigmatic part of the collection, because each one represents a book that was on a shelf in an ancient library that has a text that is completely unknown. If you want to see what one of these looks like, I'd like to pass a model around. You'll find out in a minute about how I got an accurate model. Laurel, if you could come and grab this. This is one of the books from Herculaneum. It's an exact replica. It's printed in plastic, so please don't worry if you drop it, it'll be fine. And you can get a sense of the heft and also the size of the papyrus that represents that book. Finally, there was material called desegni, which means sort of sketch or drawing, and this sketch or drawing was made when the scrolls were opened, and often the scroll fragments were scraped completely away, lost to antiquity, and only what remains is the sketch. These were the methods that were applied to the Herculaneum collection, and they present these huge material challenges. The open trays, like the one on the first slide, there are 3,500 of those. They're difficult to read, they're fragile, and they're also very difficult to separate because layers still are stuck together. The scorza, which represents all of the bits that have fallen off and large chunks, there are approximately 100 trays of those individual pieces. They are also fragile. It's also very difficult to put the pieces back together because they're fragmentary and in no particular order. The disegni are distinct from all the images, and they're difficult to view because you don't have them aligned with any existing papyrus, because they threw the papyrus away as they made those drawings. And then finally we have the intact scrolls, approximately 300 or 400 of them in various states of fragmentation. Some of them are whole, like the one that's going around. Some of them are probably pieces of a scroll that's been broken in two. Let me frame this with a timeline so that you can understand the scope of my entry into this world over the last 4 decades worth of work. If you're a fan of computed tomography, I'll be talking about it in a little bit, and we can have some fun with it. The first application of computed tomography in antiquities was in 1979, right about the time that the inventors won the Nobel Prize in Medicine for inventing and applying the technology. About the next decade was the end of the physical unwrapping. Between 80 and 90, Marcello Gigante, who founded the Centro, which is the center that holds the material in Naples, stopped and halted all physical unwrapping in that decade. I have to put a red star where the internet occurs so that you can realize that was where I entered the picture with the beautiful Mac 1995 version of the Beowulf, the electronic Beowulf. And it was near the end of that I began the technical work of digital restoration, and in particular virtual flattening. So let me talk about virtual flattening first, because that's the precursor to unwrapping. This manuscript from the Marciana Library is unique. It was spirited out of Constantinople by Cardinal Bessarion before Constantinople fell, and became a core part of the Marciana Library's collection, it and other volumes that were managed to be saved. It's on parchment, it's beautifully bound, and the only facsimile that existed of this manuscript before we did this work was a photographic facsimile by an Italian by the name of Comparetti in 1901. You can see that the pages are not flat, and from Comparetti's facsimile, you see the readability that was achieved with the 1901 lens and photographic system of the day. We were able to image with a high-resolution photographic back that gave us beautiful color. In particular, scholars were delighted to know that actually some of the things were in different colors, which you couldn't tell from Comparetti's facsimile. Obviously, if you were able to see the original manuscript, it was possible to confirm and verify various things. But what we were interested in this project is digital restoration, not just facsimile, but the next step forward. Would it be possible to make the pages appear flat, even though we photographed them in a disposition when they were not flat? It turns out that you can't do what Comparetti did, which was slice off the binding, go out into the plaza, press everything flat under the glass, and use the sunlight to get great lighting. What we did instead is that we imaged all of the pages in place, captured a shape model, and then built a digital restoration possibility of flattening, virtual flattening. And you saw that playing out. So how does that relate to Herculaneum? Well, the wreck of Herculaneum deserves a little bit more attention. Wordsworth himself wrote this poem in 1819. O ye who patiently explore the wreck of Herculaneum lore, what rapture could ye seize some Theban fragment, or unroll one precious, tender-hearted scroll of pure Simonides? September 1819, Joseph Henry, Albany School. He was 19, 20. He became faculty there. That's the time scale that we're talking about. The first president of the Smithsonian and the long-term president of this society was in school when this poem was written. And then if we reverse time to the actual cataclysm, AD 79 is when we know that Herculaneum actually exploded. And the two towns that are most famous on the map you see to the south, planned south, you see Pompeii. But toward Naples, you see the town of Herculaneum, which it was a seaside luxury resort. It was Herculaneum that actually had the library. Not much written material was discovered in Pompeii for various reasons, but in Herculaneum you have the Villa of the Papyri, and that villa created for us this enigmatic collection that everyone of the day was incredibly interested in working with, and in particular, Sir Humphrey Davy. Here's a letter written in his own hand. He was the head of the Royal Society at the time. He writes this letter to his colleague, and he says, Lady Davy, who's going to make an excursion in France, lucky lady, I'm sorry to say, in consequence of an obstinate cough and by the advice of her physician, will deliver to you the papyri which you entrusted to my care in Paris. I have unrolled a part of the fragment, which in appearance was the worst. It turns out to be a Greek manuscript, and not, as Mr. Hayter expected, Punic, but from the fragments which have been examined, of no value, and a pseudo-metaphysical work, probably of Philodemus. So not a fan of Greek Epicurean philosophy. But here's something interesting. I have little doubt that the bad faith of the Neapolitan sfolgatori, who I dare say from profession as well as principle is of the Carbonized school, led them to select the worst specimens as presents, lest discoveries should be made of the National Museum. I never thought to actually blame the Italians for the trouble that I had reading Herculaneum scrolls. But here's Humphrey Davy back in 1821 doing the very same thing. He tried to unroll a bunch of these scrolls and was largely unsuccessful and was very disappointed by it. In fact, Wordsworth wrote that poem because they were friends, and he really wanted to see Davy's success. The scrolls have been opened, and if you want to see a little bit piece about opening the scrolls, check out The Daily Show, and you'll find a great comedy piece where they get the crowd to actually chant, "Open the scrolls, open the scrolls." Well, guess what? They did, and when they opened them, they found fragmentary literary Greek and Roman material with titles like On the Good King, according to Homer, on Epicurus, on rhetoric, on poems, on piety. There's still hundreds of unopened scrolls, but the ones that have been opened give us the indication of what's there. And almost every one of these works is unique from antiquity. It's not copied by medieval scribes. In fact, it's a unique work. So the Herculaneum Library is incredibly unique and interesting, and the scholars estimate that if we edited everything that we could extract from the existing collection at 200 words per page, a couple of hundred, maybe 250 pages per volume, we'd get maybe 8,000 pages of edited text. And that's maybe, this is as close to math as I get, 1.6 million words in the corpus. Comparing that not in quality, but in quantity to the complete works of Shakespeare. Anybody have a guess? Shakespeare's half of that. So there you have the possible payoff from this collection, words that we have not yet extracted the total amount from the Herculaneum collection. So that gives you kind of the materiality and what's at stake with Herculaneum. We started the scientific work of virtual unwrapping soon after our virtual flattening in shortly after the year 2000, and this was just after I received the letter from Cheryl Sechrist. This is our first experiment with virtual unwrapping. On the left, you see a proxy I made in the medical CT scanner in the basement of the University of Kentucky. And on the right, you see the data from that scan. So since you've seen all the data, I would expect that you can now tell me what it says, which is exactly the problem, right? It's interesting because the content is there, the information is there, it's in the wrong form. We use a diminished imaging method, tomography, to get not what we actually want, but then we build algorithms to get what we want from that diminished modality. Why do we have to use that diminished modality? Well, we can't open things, and so we have to do something non-invasive. And so that's the game. By putting that material together digitally into a complete unwrapping instead of just a flattening, you can see the progression now, right, of the basic technical work that says, let's pretend we have a complete 3D surface, not just a 2D flattening problem. And let's build the 3D surface that represents something inside the scan, and then let's unfurl it like a flag. On the left, I have a photograph, and then two versions of what I extract from the data alone to compare to the photograph. Had I known I would be giving the 93rd Joseph Henry Lecture in 2024, I would not have done such a boring 1, 2, 3, X, Y, Z sort of pattern, but we didn't know that was going to happen. We developed the idea of virtual unwrapping based on two really important pieces of technology that we adopted and then modified. Computed tomography, using a bench source at the time at about 25 micron resolution. The medical scanner is millimeter scale, and we needed micron scale. Incident energies in the 50 kV range, and then scan protocols that we experimented with based on the material at hand. Then at the time, we required what essentially was massive computing to be able to do the filtered back projection reconstruction. Everybody was running, basically Linux clusters, and we were too, to be able to do this work. And then one upgrade, I see some heads nodding, was to put GPUs in those Linux clusters. Okay, so this was the progression. And then on the graphics vision side, segmentation, texturing, and then physical modeling for be able to do the unwrapping that I just showed you. So all of these algorithms represented the base plate scientific work that we were doing to try to make this pipeline real. Here's just an example of the constrained mapping to do the virtual unwrapping. Imagine that you've captured a three-dimensional shape. It's fixed and rigid. It's represented by M, and then you want to compute some kind of function f or transformation f that flattens that, or basically figures out the conformal map that takes the 3D shape and pushes it to a plane and minimizes the distortion in doing it so that you end up with flattened version S. And then you can imagine all the textures from the original 3D following along to create a new image on S. Okay, the constraint is that you want to minimize distortion, and our first implementation of this was to basically implement it as a physical system. So we divided the surface into small points that we simulated as particles, and we connected all the points with springs, and then we ran an iterative solution to the differential equations that governed how all of that should move if they observed physical properties of rigidity and a little bit of flexibility and collision with some kind of a plane. And that was what you saw running, and it led to what I now call an engine for discovery, because the steps that emerged from acquisition, which was the actual scanning, included then the segmentation, texturing, flattening, and then merging of all of the pieces to be able to get a completely unwrapped thing from the scan of something without ever having opened it. So I hate to take some of the magic away by saying that it's just science. So in a minute, maybe I'll show you something that looks a little bit more magical, but for the time being, here's an example from a real scroll on the right that shows a segment of it in green being located by an algorithm and then building that shape that comes out as a 3D sort of potato chip from the interior. If it's localized properly, that potato chip is going to have a texture on it that comes from the original scan, and the texture is what we seek. It's where the writing is. And then taking that potato chip with the texture and flattening it using this simulation creates the ultimate image that we desire, which is the readable version of what's inside that scroll. I'm going to narrate this because I may have lost some of you. I care about the plus ones. I care about the plus ones, okay? If you imagine the substrate that you're writing on, the papyrus, as the white dough, and then the letter pi is the writing, and it's in red. And then you imagine you roll that up into a scroll, and then it gets damaged because we bake it, and now you can't open it again, right? What tomography is going to give you is what you would get if you took that roll and you sliced it, and you looked at the slices end on. That's basically what the technology gives you. It's not exactly what you want. You would rather have an image just of the inside. But the way tomography works, you get these slice views. Okay, so what we're going to do with this slice is capture an image of each one of them, and of course we're going to pretend, since this is X-ray, that we don't have the color. Okay, so the X-ray gives us kind of an intensity value, not a true color value. And then we're going to segment, which is to find where that roll surface actually is, and then build what we get from each of those slices. And when we put it back together, what do you think we're going to see? The letter pi. It has to be there. So if all of those things are true, we can see the slices, we can find the thing, we can trace it through, then we can do this. And I'd like to thank my son, who was in high school at the time, Jesse Seales, for doing this stop motion video. It took him all day so that you could enjoy a minute of video. He really did do a brilliant job, because I think it gives you a good intuition about how the tomography is mapping on, and that's going to be important for the sequel, because I want you to see now some real data from Herculaneum. And these are not tender-hearted scrolls. I don't know what Wordsworth was saying, you know. These are hard-hearted scrolls, okay? On the left is a scroll being imaged on its exterior with some lasers so that we could create cases. And the second thing I'm going to pass around, Laurel, if you could help me again, is another replica of a scroll that's actually in one of the cases that we made, so that you can see how we transport them safely. And on the right, you see the vision. The vision is virtual unwrapping. Well, here was the first experiment we did with a real scroll in 2009 at the Institut de France, which has 6 scrolls from Herculaneum that Napoleon acquired during the Italian campaign and ended up in the Institut de France. On the right, you see a radiograph. On the left, you see a center portion of the reconstructed version. And you see Madame, what is Madame's name? I've forgotten now. The librarian, Madame Carew, placing the scroll into the machine that we had at the time, which was this benchtop source from Skyscan. And what happened on this example is that we've utterly failed to even segment this layers. I don't think you can even do that with your eyes. And if you can't do it with your eyes, then you probably can't do it with software. And certainly at the time, it was pre-AI. We just didn't have a solution for a complete segmentation to even get started on virtual unwrapping. At the time, if you Googled my name with the word stymied, this article would come up, a really nice article that they wrote about me in the press in Lexington about how we weren't making any progress. And this is one of the cases where it wasn't fake news. It was actually right, and I don't know if this is still up. Please don't Google it. But later, as we continued the work, even the bigger publications that were fascinated by our efforts wrote things like this. The New Yorker, John Seabrook, "I do not expect this scroll will be read during my lifetime," Delattre said finally. He closed the lid of the small box with both hands, his shoulders slumped in defeat. "I'm sorry I ruined the ending for you, but that was how he closed the piece." Yeah, that was it. I guess that's how they roll in New York. I don't know. What he wrote about me in this piece was that Brent Seales, who was denied the scientific glory of being the first to see the inside of the rolled scrolls, had been focusing on the software side of the problem. Well, I call it the science side of the problem, okay? And yes, it involves software, but look, we were imaging with tomography, and we needed to solve these scientific problems of segmentation, simulation of the flattening, right? So that we could then manage all of this data and be able to see the ink. So yes, we went after it, but there was something that was missing. Something that was missing that was actually really important, and this was 2015. And the first thing that was missing was a success. And we got it with the scroll from En-Gedi. So let me shift gears for just a minute and talk about the scroll from En-Gedi. We'll come back to Herculaneum. I'm going to pass around a replica of this scroll. Laurel, I'm keeping you busy. I'm sorry. Because this is really interesting. It's literally the size of a magic marker or a small cigar, not even a big cigar. We didn't know this scroll existed. It came to us from the Israel Antiquities Authority after having banged our heads against the Herculaneum wall they were aware and they thought, well, maybe the Seales research group can give this a try. They scanned it themselves, and it's really interesting. It was found in En-Gedi at an archaeological site on the western shore of the Dead Sea in 1970. And En-Gedi, of course, is referred to in the Bible in 1 Samuel 24:1, where it says, after Saul returned from pursuing the Philistines, he was told, David is in the desert of En-Gedi. And you can read the story about how they chased each other around. It's a famous place. The scrolls were not part of the Dead Sea Scroll collection per se, because they were found down the road a little bit from Qumran. But of course, the world was reverberating with the discovery of the Dead Sea Scrolls. Here you see the museum where it had everything laid out and they were managing all the fragments. And, it was a different era. This is not how I look when I work in my lab. But I suppose, in the 50s, right? And this picture comes from a marvelous piece that was written by Edmund Wilson for The New Yorker. And it's extensive and wonderful, but here's an interesting quote if you want to explore this later. Wilson actually conflates both Herculaneum and Dead Sea Scrolls in one quote. He says, "The outsider cannot but be struck by the frequent reluctance of the learned world to recognize important discoveries. In connection with the failure of scholars to first recognize, then to acknowledge the antiquity of the Dead Sea Scrolls, Professor Albright of Johns Hopkins has pointed out that the discovery of Pompeii and Herculaneum was in its time relegated to the realm of fiction by outstanding personages." Well, I can't tell you how long I lived in the world of fiction where people would just say, yeah, you're going to read inside a Herculaneum scroll. By the end of tonight's lecture, you'll see that we've done exactly that. At the site of where this scroll was found, you can still go today and see the beautiful mosaic floor. It's a national park. And at the end of the mosaic floor, the place where the Holy Ark was discovered. And the Holy Ark, when it was uncovered by the archaeologists, looked like this. Not much, but archaeologists have the glasses to be able to see what is actually there. Sefi Parath pulled this scroll from the ground with his own hands, and Penina Shore gave me the data on a hard drive in 2015. And our software, which we called Volume Cartographer, the icon of which is on the right, was mature enough that we were able to completely unwrap everything inside this scroll. And you see that it's not papyrus, it's animal skin, but it was the victory that we needed. That was the thing that was missing. Our first attempt looked like this, and while you can't see a perfect text, you can see that there is writing and that it is Hebrew. Our next attempt, which appeared on the front page of the New York Times, was this. And if you look at the scallops on the top, you can count the divots that represent the wraps that we unwrapped. 1, 2, 3, 4, 5 wraps. That's where parts of the scroll are missing, and then the virtual unwrapping follows the material so that you can see the shape as it unrolls. The scale is very small, and that's a scale replica. What this manuscript turned out to be.
Virtual unwrapping begins by acquiring a three-dimensional volumetric scan of the damaged manuscript. This scan produces a set of cross-sectional images that show the internal structure of the scroll. When viewed as a 3D object, one can clearly see the individual layers of the scroll, but any text on the surface of those layers is obscured from view. In order for a readable version of the scroll to be produced, these images must be passed through our virtual unwrapping pipeline. First, we capture the 3D shape of the layers of the scroll in a process called segmentation. On the left side of the screen, the software moves through the scroll, image by image, tracing the shape of a single scroll wrap. On the right, we see the 3D model that this produces. Next, we extract the ink from the data in a process called texturing. Using the 3D shape generated by segmentation, our software makes another pass through the scroll, this time looking for very bright pixels. Bright pixels indicate regions of dense material, in this case, inks made with iron or lead. We now have a single wrap of the scroll with the text shown clearly on its surface. However, because the surface is curved, it's difficult to read all of the text from one viewpoint. The flattening stage of our pipeline converts this textured 3D surface into a flat plane so that the text can be more easily read. To produce the best results, these 3 steps must be performed on one small section of the scroll at a time. As a result, we end up with several texture images that must be merged together. This merging process creates a single consolidated image that shows the full text. Using this pipeline, we have restored and revealed the text of 5 complete wraps of the En-Gedi scroll. The 2 distinct columns of Hebrew writing reveal the scroll to be the book of Leviticus. This marks the En-Gedi scroll as the earliest copy of a Pentateuchal book ever found in a holy ark, a significant discovery in biblical archaeology.
It was the victory we needed. It was a beautiful result. And thank you to my daughter who did the voiceover for the wonderful price I will not disclose. But we had data that was beautiful, and we also had a success applied on a real object that was of significance, of real historical significance. For example, we did some analysis of our flattening algorithms to see, because now we have text, we can measure distortion. So we can see with heat maps which mappings are working, assuming that the mapping from the 3D structure that is segmented to a 2D plane is conformal. Assumes that you can find a conformal map, but that's not necessarily true if there's been strange distortion. You can imagine taking a half sphere and trying to make it planar. You have to create distortion somewhere. So we measured some of that. We wrote a paper. But what was really interesting is that the Dead Sea Scrolls at the Second Temple period sort of created a moment of almost silence between that and the Venetus A. And the En-Gedi scroll actually sits right in that period. It's not actually in the Dead Sea Scroll collection, but it's very early. And some of us actually suspect that, like the gavel, the scroll is actually much older than the archaeological site where it was discovered. Okay? So we wrote a paper with the biblical scholars who are amazing at Hebrew University, an early Leviticus scroll from En-Gedi. And they produced a complete transcription of what's readable. And of course, if you know the text of Leviticus, you'll know that the first chapter is about burnt offerings. I see no irony in that at all, do you? But I also love the first verse where it says, "The Lord called to Moses and spoke to him from the tent of meeting." So what you've got there is a God who talks to people and calls them by name and doesn't just speak, but calls. I think that's pretty interesting. Okay, so now I'm back to Herculaneum for a rousing conclusion for this talk, and then some Q&A. The sticking point with Herculaneum was always that the ink wasn't of the right chemistry to do what we wanted with tomography. We call this the carbon ink challenge, but on the left you see a very small fragment with a letter form. It's a lunate sigma, so it's a sigma, but it was sort of the old form before they modernized. And on the right, you see what that looks like in tomography, and you can't see any evidence with your naked eye in the tomography. So if you're doing this experiment and you're in the lab, you just say this is a failure. We scanned it and we can't see it. And by contrast, medieval fragments that are written with iron gall look great when you scan them with X-ray because they have iron in the ink. X-ray loves iron. So we call this the carbon ink challenge, and the missing ingredient is deep learning. Here's what we observed in late 2015, 2016. We observed that there's evidence of the ink in the tomography, but you can't see it with the naked eye. How do we figure that out? Because everyone else, the conventional wisdom, was that you will never see tomography, you will never see the ink because it's carbon-based with tomography. Well, what we did is we just put a bunch of carbon on paper and we scanned it and we said, well, we can see the ink. But what we were seeing was the shape change, not necessarily a density change. Okay? So the conventional wisdom was that we weren't going to succeed unless we had metal in the ink. Conventional wisdom was that the scroll from En-Gedi was a fluke and that we were just lucky and that most material is not going to be in the right category, so good luck with that. I mean, I talked to my Israeli friends about that, and they said, it's not luck. It was Leviticus. If it was luck, you would have gotten Exodus. You know what you're talking about. So carbon ink is not invisible with tomography, and what we discovered from all of our experiments is how to make the evidence of the ink, which is not there for the naked eye, to become visible using AI techniques. Here's a scanning electron microscope view of a very small fragment. The photograph on the right, in the center, a sketch, so that we have a reference of where the ink actually is, and you can see sort of the ink shaded as a slash across there. And then the scanning electron microscope shows very nice, a sort of different texture where the ink is kind of in profile, sitting up above the papyrus, right? The emerging principle that we discovered was that the ink on the substrate changes the shape of the surface. It might only be small, but it does. And in order to see those small changes that are shape-based, not density-based, we needed some kind of high-resolution scan. We probably hadn't had enough resolution. And then the third thing, we need to detect that, and we believed that AI and the emerging framework for AI was going to be the thing to do it. And the more we did experiments, the more we became convinced. I mean, take a look at this scanning electron microscope view of ink, no ink, blank papyrus on the top. And you see this is a close-up of the ink. That texture looks completely different, and the features of it, right, look completely different from these features, which is just this raw papyrus. So what we figured is that we could train an AI system to recognize those textures if we could simply set up a system where we could capture the data in high enough resolution and then do the training. And that's exactly what we went after doing. The first thing we did is we published these preliminary results. So they were results, but they were on a very small fragment. They weren't on a whole scroll, and they were on a proxy that we made so that we could control things. With the proxy, what we did is we built a table that increased the amount of ink with every column so that we could sort of see the ink disappear as it got thinner and thinner. And that gave us some idea of where the knee in the curve of resolution would be so that we knew what we had to get when we went to scan the Herculaneum scrolls. Of course, our conclusion in this paper, which says this previously unseen evidence of carbon inks, which now can successfully be made visible, is a discovery that can lead directly to the non-invasive digital recovery of the lost texts of Herculaneum. This what I think is an amazing conclusion in this paper led to exactly 0 hits from anyone. No one cared because we didn't reveal anything from the ancient world. We just said, we have a recipe now. We think we can do it. But what we did is we went after some data. So we saddled up and went out to Diamond Light Source, which is outside of Oxford, and it's a synchrotron. And the reason we went to Oxford with Herculaneum material and used a synchrotron is because high energy physics in the form of a beam that comes off of an electron ring, this is what the synchrotron looks like, allows very precise control of the incident beam and probably would help us generate the spatial resolution that we needed to capture a data set that would actually work. This setup inside the hutch was complicated. You see, in the case, we have the scroll. It's mounted and ends up in an amount of equipment that's astonishing, where the incident beam, millions of times brighter than the sun, excuse me, illuminates the case, and allows us to perform tomography, but not from a bench source. It's tomography from a parallel beam that gives us the chance to compute very high resolution results. And when you see the resolution, I think you also will be astonished. Resolution, regularization, and rigor were our key achievements over the last 5 years that have led to the breakthrough that I will feature tonight. First, resolution. In the hutch, you see me with Madame Bérard from the Institut de France, and inside that case is a completely intact Herculaneum scroll. It's the one we've read. So now we know what's inside it. What we worked out on the board of the control room is a number of different incident energies, the modules that would capture the images, because they have different spatial resolutions, and the time that it would take to do that. And in particular, we worked out a way to do what's called an annular scan. So we could actually short circuit the time it would take to do all of the rotations. with a parallel beam as opposed to a cone beam, which comes at the sample at an angle. A parallel beam allows you to reflect its passage through one side and create a double wide sinogram, a double wide projection from only a single set of rotations. And if you do that twice, you actually sort of save half the time. What we were having trouble with is thermal effects that make everything move if you take too long to actually do the scan. You also see on the left that we had to divide the sample vertically into multiple slabs and then reassemble all of that into a single data set at the end. So we had, in the end, we were able to achieve 7.9 micron voxel size using the parallel beam, annular scans, and multiple slabs. Here's the visual result. On the left, 25 microns from 2009. You ready for this? Yeah, it's better. It's better. When we collected this data, this is the central part of the scroll. There's writing on that papyrus, we know now. When we collected this data, we knew that we probably had what we needed. This hurricane represented the highest spatial resolution scan anyone had ever achieved on a Herculaneum scroll. And I just want you to appreciate the trade-off between the 8 micron resolution and the size of the scroll, which you have in your hands. Those two things are incompatible. And so collecting that was a major step forward. If you slice it the other way, not edge on, but like a banana split, you get this view, and you see that Humphrey Davy was never going to be able to unroll this scroll, right? Not possible. The geometry is sort of messed up in all directions. So we had to also figure out how to regularize our data. Regularization means that the software needed to be predictable and repeatable for a large number of experimental management cycles. And we also needed to manage that data in a way where we could keep track of all of the many layers, all of the crazy resolution. So while we were doing the regularization, we also hunted quite often for seeing if we could see visible things in the data. And it turned out at the 8 micron resolution, it was possible sometimes to see the ink and evidence of it with the naked eye. And this will be important when I talk about the contest. But you can see examples here on the left where the X-ray correlates very nicely with a photograph that we have of the ink on, say, a visible layer. But then there were times when it didn't correlate very well. And so we realized we were really 8 microns is probably right on the edge of visibility. It's sort of a yes-no kind of a thing. Here's an example of a wrap from inside that we began to virtually unwrap, and you can see a section like this where, can you see the mud crackle? It's probably evidence of ink that was placed over the grid of the papyrus, which is orthogonal layers in 2 different directions. And anything that interrupts that pattern is something that the machine learning can actually learn. So we created a structured way to run experiments on open fragments so that we could verify the machine learning converging with labels so that we could do the science. So you see the labels on the right, which are the answer, and the machine learning trying to learn the ink on the left. Essentially, this was the framework for our approach. We take a fragment and we photograph its visible portions. And then we also have the tomography of the entire fragment. Tomography being on the bottom part of the middle of the photo. Now we have a roadmap where all of the ink is located in the tomography because we can align the photograph with the tomography. So even though you can't see it with the naked eye, we have a label set that allows us to train the machine learning system to learn that ink. Here's the training. Think about the middle network as really just a 3D convolutional neural network, a fully connected final layer with some kind of softmax. Oh, it's just a machine learning thing, okay? And at the end of the training on the top, we can take a fragment we haven't seen before and basically do the inference. And if it's learned the difference between when it has ink and when it doesn't have ink, you can basically infer from a segment that you've never seen what that looks like. And I'm going to skip some of the geometry and just talk about hyperparameters being really important in the way, this is why it took the 5 years, because we have all this data, it's massive, and then we have to use that data to figure out how to structure the network, set up the proper hyperparameters, and maybe even search for a key neuron that's going to encode where the ink is. Finally, we approached the entire thing very rigorously, because at the end of the day, think about it, I'm telling you what's written inside a scroll that you can never open and you can never see. How are you going to have any trust in that? Well, you can actually have trust in it if the experimental slate is rigorous and can be inspected by third parties. So this experimental slate is inspectable and formal, but like we basically have everything stored, and any peer reviewer can take a look at this. Here's just a depiction of the small subvolumes that represent the training sections from the tomography, the convolutional neural network, and then a twofold experiment on a fragment. So the fragment is colored blue on top and orange on the bottom. One is used as training, one is used as inference, and then you can see the experiment basically run. So for example, the trajectory of our work went from the target we made to a very small twofold fragment, to 4 fragments that we scanned at Oxford, to a complete set of dialed-in results that prepared us for the next step of this work. And here's where we were when we started that next step. Visible layer, layer underneath, inference. The layer underneath has ink, and as my graduate student said, it says hi. Actually, some ink responded. It wasn't the perfect result that we wanted, but we knew that this was going to work. Okay, so we have a complete framework in hand. And unlike John Seabrook, when Jo Marchant wrote about this in the Smithsonian, she said this: belief returned to his wide hazel eyes. I refuse to accept that it's not possible, he said. At every turn, there's been something that opened up. And what opened up was machine learning, and then the Vesuvius Challenge. Vesuvius Challenge was an opportunity that I had to team up with partners in Silicon Valley who were able to raise a $1 million prize pool for us to offer competitors to work with us to do the next steps. The Vesuvius Challenge, conceived by Nat Friedman and founded by him and Daniel Gross and myself, included a huge team both of investors and also researchers who helped us run this competition and ultimately give away a grand prize of $700,000. Let me tell you what we were after with the Vesuvius Challenge. If you have graduate students working on a project, on the cost axis, they're a little cheaper, but probably not as rigorous as you would like, although over time they become more expensive and more rigorous, right? Employees, they're on the upper right. They're expensive, but they're the most rigorous and serious people you're going to get until after a while. Maybe we all know sometimes that happens, right? What we were looking for is, somewhere on the lower left or upper left. Crowdsourcing could be a possibility, but over time, it becomes more expensive and maybe you don't get the rigor. And then finally, the contest gave us a point on this graph where we thought it could be interesting. Serious competitors who are after a prize and maybe more expensive, but if Silicon Valley partners are paying for that expense and I'm not writing a grant proposal to the NSF to try to make that case, that might be a good thing. So we launched this contest last year on, actually with $250,000 prize pool that in 1 week doubled and then doubled again. And we launched on March 15th. March 14th was the launch of GPT-4. So I just want to say the Ides of March, it's just not good. Just should have thought about that. The Vesuvius Challenge recovered from the launch. We raised more than $1 million total purse. And what it required of us was all our code, all our data, tutorials with the help of Nat and Daniel that explained everything, and then paid workers to brute force some things that we knew the competitors were not going to do. So that's a lot, right? What did the competitors do? Well, what they did is they took an AI-based approach to things that we laid out, and they trained independently on a huge amount of data, improving hyperparameters, improving software tools, and then building a community of more than 2,000 people who talked with each other about this work constantly, and then ultimately revealed text from within a scroll for the first time in history. What were some of the risks? Well, we weren't sure, we being me and my research team, whether our stakeholders would actually understand what we were doing. The university, people who had invested in our work. What if the challenge ended up being too easy and some person did it in a day? What would I say then? You know? Well, they would be giving the Joseph Henry lecture, right? So, well, what if it was too hard and we couldn't get anyone to win? We wanted to give away the money, and that would be maybe embarrassing. And what if, in the end, it's not scientific? I'm giving you tonight a talk about science, and we wanted the results to be durable and rigorous. And then, of course, what if people make fun of you? You have to go back and look at this piece because the comment was, wow, the first word that they revealed, purple. Nice. Okay? It was purple, actually. We had a first letters prize, and we offered $50,000 for whoever could meet our standard, which was a certain number of letters within a certain area. And this won. And I think there's a Greek physicist in the audience who can read this. Raise your hand. Yes, there you are. Yes, it does. Porphyra means purple. And what actually happened on the first letters prize is that they revealed evidence of 4 columns, the winning part of which was only a portion. At this point in October, everyone was going crazy because we realized we'd unlocked it, like it was happening. This was how much we actually were going to segment. Can you see the scallops on the top? Remember how we counted those on the Engedi scroll? Okay, well, good luck counting those quickly. But it's 20 wraps, maybe 25. The competitors were running over some or all of these to be able to run their AI, competing frantically with each other. Because what we'd done is we had hired a team to actually segment all of those, so the competitors just focused on the AI. They just made the evidence of the ink appear as robustly as possible on what we segmented from that scan. And so here is a graph of the surface area of the segmented results over time. And you see, we launched on the Ides of March before May 1st. We had very little available. We thought maybe the competitors should do this work because they're winning money. And then we thought maybe we should go ahead and segment all the work and let them just focus on the AI. And so that's what we did. The segmentation team segmented all of that. It generated quite a bit of news coverage in October. And one of the pieces that I really liked a lot was the New York Times Hard Fork article that picked us as a 2023 Good Tech Award. So check that out because I thought it was quite a nice piece and it was a little bit longer. University of Kentucky also put me on their website, which I was happy to see on my cell phone, reminding me of one of my favorite movies. So that was also gratifying. Take a look at the award ceremony that we hosted at the Getty Villa on March 16th. And you'll find the grand prize winners celebrating receiving their checks. Grand prize winning $700,000. This video is available at this link, The Vesuvius Challenge, Resurrecting a Library of Ancient Scrolls. I want you to see this video. This was when we told the winning team that they'd won, okay? And Youssef was not able to be at the ceremony, but you can see him on top. He's Egyptian. He says, we invented papyrus. Like, he's just all in. He's just all in. I mean, that's just wonderful. Okay, so yeah, if you graph the characters revealed non-invasively over my timeline, we have 0, and then 0, and then 0, and then a half, and then 2, and then 10, first letters, and now we're exponential, and you see the hockey stick. But what we actually think is happening is that the hockey stick goes this way, because there are 300 more scrolls. So if you want to see what the scrolls say, go to scrollprize.org, and there's a nice expose, scrollprize.org. But what I'll show you is this: pleasure, abundance, and scarcity. This is probably an Epicurean work. It might be by Philodemus, although people are not sure. And it tries to pose and then answer questions like, do things that are available in lesser quantities afford more pleasure than those available in abundance? And what the text says is, this is transcribed and then translated. As too in the case of food, we do not right away believe things that are scarce to be absolutely more pleasant than those which are abundant. Such questions will be considered frequently. Okay, so you see our experimental layout. We've done ablation studies. Let me conclude by saying that Wordsworth's poem was the second to the last stanza. The last stanza is that we're indeed a genuine birth of poesy, a bursting forth of genius from the dust. What Horace gloried to behold, what Maro loved, shall we unfold. Can haughty time be just? Can haughty time be just? I think that a lot of physicists have asked this very question, right? Well, what about that? The world takes things away from us, doesn't it? But tonight I'm proclaiming Herculaneum scrolls unlost, because we can take parts of it and we can read it. And tonight I am also reminding us that these are stories. This letter is now in a library in Maryland, and the replica is on the wall. Can't be harmed. Can always make another one. It reminds Cheryl of the sacred bond between author and reader, where the author was her dad and she was the reader. He did come home from the war, and they spent many happy times together. And the reason that she had the letter on her wall is because she loved that moment. She loved that her father did that. And her father became the local postman, delivering letters all over central Maryland. Thank you very much.
Wow. So we have time for some questions. When I call on you, please stand up. Tell us your name. Tell us if you're a member, and then ask a question. Save your speeches for later during the social hour. Let's start with the red microphone.
My name is Paulos. I'm not a member. Now, you mentioned that one of your seminal works was deciphering the Beowulf paper or Beowulf manuscript. Now, I happen to, and you also said that you use Linux clusters. Now, I happen to know that in the 90s, one of the earliest projects of clustering Linux computers was called the Beowulf Project. Now, could it have been inspired, named after your work?
I don't know how the naming went. I know that the electronic Beowulf was originated at the University of Kentucky by a medievalist. I was a junior professor and jumped in. I know what you're talking about, the Beowulf cluster work, and I really don't know how tangled or untangled they were.
Blue microphone, Frederica.
Yes, I'm Frederica Derima, and I'm a member. Such a wonderful work, and I have many questions, including how far we are from being able to translate. I mean, you think with AI, you should be able to translate anything that you scan very quickly, so we can start learning about history, because I think it's such a fortuitous kind of occurrence that we do have this papyri now, and I think can fill a big gap in parts of the history, both Roman and Greek. I also have a scientific question. It seems that the writing on the papyri that were like based on a goat skin used different ink, as you said, iron or lead, and this uses carbon, but maybe there are other materials. So Is the scanning because of the scattering on the carbon material? Is it because the papyrus, when the ink impregnates it, kind of puffs up and changes the dimension? So what is the scanning measure? Do you know?
Okay, first question first. It's an interesting moment for papyrology. Papyrologists actually don't want AI to do the transcription and the translation because they are papyrologists. And it hasn't been actually since Poggio Bracciolini in the early Italian Renaissance that it's been possible that maybe we will have new material from the ancient world, from the classical world, authentic original material. He ran around, as you know, from the Swerve and other things that you may have read, and collected those medieval manuscripts so that they wouldn't be lost. And we feel like we're at a 600-year high in this moment, and I don't think that the papyrologists want to give that up to AI. They have been waiting for this moment to be able to have new material instead of simply re-editing something somebody already edited. So you can imagine that the junior papyrologists are over the moon at what their field might look like in 10 years when we can release this data. The second question, we don't actually know exactly what the machine learning is doing. It's actually collecting evidence of the ink from a number of different signals, and there are three that we know of. There is a slight density change because there is more carbon in the places where there's ink. There's a slight deflection of the beam. It's a refraction index, and you can play with that using something called phase contrast tomography. And because we have a propagation distance, we're actually able to see a little bit of an effect from that. And then we do have morphological features where things are thicker, they're thinner, and there's a statistical difference in the way that the grid, when it's coded, right, appears. Those are the three things that we think are confused in what the machine learning is doing. And this is one of those places where the black box might or might not let us tease that out. Thank you.
Yeah. Thank you. So the diamond machine is at Hardwell.
Last
right?
question.
Right. The diamond machine is at Hardwell, and I was wondering if they also have, capabilities for material characterization, so they can assess, or otherwise the synchrotron at Brookhaven that I mentioned to you earlier on might be a good source for.
Yeah, thank you for that. We have not done a complete characterization of the visible ink, and that's a really interesting next step.
Yeah. Okay. Thank you.
I want to sneak a question in here. Is the LCLS at Stanford able to provide you with more resolution?
We did some really work at SLAC. You mean SLAC? The
Yeah.
Linear accelerator?
Yeah, they have the very, very high intensity, very, very short.
I haven't been back to any
Toast.
American synchrotron, and the reason why is because the materials are all in Europe. And it's easier to stay within the EU than it is to come to America. It's difficult, right?
There is another free electron laser along the lines of the one at SLAC in, I think it's Heidelberg.
Thank you. Super fascinating. My name's David, not a member. This kind of builds on these questions. I hope this isn't repetitive, but essentially the question was, how are we going to get better resolution? At what point does better resolution stop yielding dividends in our ability to read additional letters that we haven't yet viewed? TSMC has some pretty crazy lasers. I mean, like, what are the fundamental barriers are we close to the fundamental barriers? And if not, what are your next steps to get to those fundamental barriers?
Right, so we don't know. At some point, higher resolution hurts you and it doesn't help you. So there's sort of a U-shaped curve, right, with resolution on the axis, and you want to find the sweet spot. It's very difficult to experiment on this data. It'll be easier in the future to do that so that we can answer those questions. We're hoping to build a field deployable system that can let us, at scale, scan everything on site. And to be able to do that, we have to answer some of those questions.
Blue microphone.
Will, not a member at all. Really, really cool. You obviously had to build a bit of a training data set to do this one scroll. Do you think you're going to have to retrain on every scroll?
We think that initially we will have to do that, and then we're hoping that we can combine into sort of an Uber network
Huge
that
data
has seen all papyrus, right?
Yeah.
So sort of like, Google Lens,
Yeah.
right? For every image, just tell us what the image is. And so we think that ultimately will happen, but right now we don't have enough data to do that.
And you have no idea what your dependencies are
Right, exactly.
on any of it,
Yeah.
basically. And then So kind of similar question to before. You can obviously buy there are people who run X-ray as a service, like CT scan as a service, like Zeiss, right? Do any of their resolution systems get anywhere near close to what you need? What is it you need, like in terms of resolution?
They're really close, but
Yeah.
geometric magnification usually is limited because of the size of the sample. You just can't get the magnification that you want for the larger scrolls.
Yeah.
But then there are these multiple stage systems where you can sort of move the sensor.
Yeah.
So you do a left-right move, but then the scan times are really high. Okay, and then the thermal effects of all of this stuff moving around. I mean, 8 microns is the size of a red blood cell.
Yeah.
So you can't have a lot of movement before your scan doesn't really give you the resolution because it's all fuzzy, right? Because everything moved.
We just ran a scan with Zeiss on a consumable cartridge that got about 20 micron, and that only cost like $1,500.
Yeah.
Just for some scale. I don't know if
Okay,
that'd be
yeah.
helpful at some point. But yeah, really cool.
Okay, thank
Awesome,
you.
man.
Red microphone somewhere?
Aki Birch, member. Can you say anything more about the nature of the text? It's a book, but what sort of book is it?
Yeah. Okay, I think it's an Epicurean text. Probably could be by Philodemus. It's not fully edited yet because it's 20 columns, and papyrologists will take a year to edit 3 columns many times. What's also interesting about the editing of the text is that papyrologists right now are working together, which they never do, because they're used to doing their work solo. Another thing about the text is that we only have the tops of the columns. So if I gave you a novel and I cut it in half, and every page you lost context halfway through, and then I asked you what's the book about, it would take you longer to tell us what the book is about. But generally what we know is that it's probably about pleasure, and the Epicureans liked talking about pleasure because the Stoics were kind of anti-pleasure. They felt like spending time on worrying about pleasure as a philosophical thing was probably not productive. And they argued about it among themselves. And that is a response from a non-papyrologist, non-classicist computer scientist, okay?
Red microphone?
Ms. Timothy Thomas, I'm a member of the society. I'm wondering about the owner of this library. What do we know about him? What was her? What were the tastes? What seems to be in the collection from what you can do? Why did he have this collection?
So there were artifacts that were discovered that were not scrolls, bronzes, marbles, and a bust of Piso Calpurnius, father-in-law of Caesar, was discovered with a name engraved. They believe it was probably his seaside palace. It's luxurious. You can learn more about that at the Getty's exhibit, Buried by Vesuvius, but I think that there's a lot that's unknown. The library is not fully excavated. So what happened during the excavation is they built some tunnels and luckily discovered a few things, but it remains largely unexcavated. So if I walked into your house and I grabbed one book, and then someone asked me, the guy who asked you that question, I'm sorry, I didn't catch your name.
Tim.
What kind of writing does he like? And I took the one book and I said, well, I guess he likes, I'm not even going to venture what that book is. But you see what I'm saying, right?
I think we're at the blue microphone.
Maria Zemankova, thank you for fantastic work for all of the years. And you had done the hard work on making it possible for the contest participants to try to read what's actually written there. And you had 3 winners. And I wonder whether you or somebody in sub-meta level tried to figure out what techniques they had used to win, or at least be 1 or 2 or 3 winners.
Yeah,
and then try to do a meta-analysis of what they had done and combine the winning techniques to do even better.
That's a great question. We've actually done better than that. We required everyone to open source everything they did, and return it to us so that we can see exactly the techniques that were happening. Nobody did any work that was a substantial departure from the trajectory we already set, but they did a ton of exploration of tuning and trying to understand, for example, the subvolumes turn out to be better if they're pancake-like. because the ink, if you have an isomorphic shape, you go too far into the layer to have that be meaningful. So everybody started using subvolumes that were wide in X and Y and not very deep in Z, which makes sense, right? Those are the kinds of things that were discovered and then were returned to the competition. I don't think that it would have worked as well if we'd let everyone work for 8 months with no communication for a grand prize, silently working. Nat Friedman and Daniel Gross and their colleagues who were working on the competition made sure that we had progress prizes and that everything got returned to the global pool. So
We'll take a couple of questions from the web, and then we'll go to the red microphone, then we'll go to the blue microphone. Web.
Questions from the web. Dave Rabinovitz, who is a member, asks, can you give us some of the hyperparameters in the winning network, such as how wide was the network, how many hidden layers were used, and did they use RELU?
yeah, so no, I can't because I don't have that information at hand. Actually, there were lots of different approaches. So what we did was a fairly basic network. That was basically a fully connected CNN, but what other people did was they tried many different network architectures, and then we got reports from the contestants to let us know how they architected their networks, what the parameters were, etc. So we have all that information, but I haven't actually digested it. There were 2,000 competitors, and we got 18 submissions for the grand prize, and it was all we could do to just make sure we were correctly awarding the grand prizes. So there's more work for us to do to assimilate everything that's been done.
Okay, we have one more question / comment from AJ Kothari. Buddhist university in Nalanda in India was burnt in 13th century by Khilji. I wonder if you can ask your colleague Bhattakara to look into if any scrolls are available for your work to decipher them.
Okay, yeah, that's an interesting point. It turns out that there are places in the world that have material, and they've carefully kept it. And we think those things will be coming forward as we are presenting options for some of their material. So I'll talk to Ankan Bhattacharya, who is my PhD student, and we'll see what he says.
Okay, we're going to go to, I guess, the red, then the blue.
Hi, I'm Andy. Thank you for your work. For one thing, I did graduate work in ancient history in the 90s, and I've been sort of following this ever since with this feeling of, is it going to come in my lifetime? And it's nice to really see results. I've got a question that is sort of in the epigraphy lane, so I don't know if that's going to work here, but I'm curious where you got your letter forms for training purposes and how much it matters. The root of my question is, obviously we have letter forms in manuscripts from the Middle Ages, and we have them in the Oxyrhynchus Papyri a century or two later than what's at Herculaneum, but we don't know what the letter forms are inside the scrolls because we can't read them. So I'm wondering if that's pertinent to what you're doing.
Yeah, that's a great question, actually. And thanks for not asking me if we would read them within your lifetime, because I used to get that question, and then I would always just ask, well, how long do you intend to live? The methods don't actually use top-down language models. So everything is bottom-up, looking just at the material in a small enough region that no letter forms are used. You can think about it as being a pointillist model that says, here's a voxel, is it ink or not? And then if you do that across the whole image, you don't need to know what language it is. The ink just appears or not, and then you read Greek or whatever's there. The papyrologists are the ones who did the reading. Now, next steps will be to integrate a top-down method that says, I know all about all ancient Greek and what it should look like. So here are the lacuna, here are the places that the AI struggled with. Go back and forth and see if you can fill in the gaps, right? There's lots of opportunity to do better. Right now, we've just broken through.
Blue microphone. Will?
Yep.
Hello.
Good evening. Hi, I'm Will Angel, a member. My question is, for the training data set, which you assembled, how much did that cost in terms of time and money? And what are your plans for improving it in the future?
We haven't added up all the costs. in time or money. Because how would you do that? This work's been going on for a while. You can go to my CV and see the funding that I've received for these various projects. You can add that up and infer, whatever you can infer from that. But I mean, what if I ask the NSF people who were here, in your portfolio, how much money have you spent on this and that and the other? And you might say, well, I don't know if I want to add that up. But it's been a lot of time because the data doesn't sort itself. And even the work that we've done at the national labs requires a fair amount of care and feeding to be able to get the reconstructions organized in a way where AI can be done. And I should just say, this is a general AI problem, okay? The jungle that is data needs to be wrangled before real AI can happen. And that's a lot of work, actually. And I think most of us who are in this field realize that. Thank you for your question.
We'll go to the red microphone, and then maybe the last question is up here in the front.
My name is
Second
Robin
row.
Phillips. I'm a non-member and a non-scientist, but I found your talk breathtaking. And I am a filmmaker, and I just wanted to say that your film, the baking film that explained the concept, was Oscar worthy. Thank you.
Thank you. I appreciate that. Thank you.
Blue microphone. I think that'll be our last question.
Hi, I'm Lillian Salonik. I'm a member. I'm wondering if, in retrospect, if the contest model was worth it or if it was even necessary. I mean, you noted that you launched the project the day after ChatGPT was launched. And so I'm wondering if, with the progression of AI models, is this something that, do you think if you had just waited, a few months, is this something that you could have, is the field of AI progressing at a rate where you could have solved the problem without the model, or was that essential to solving the problem?
Well, I think that's a good question. We agonized, when we were presented with the opportunity to work with Nat and Daniel on the contest because we had made progress and felt like we were on the edge. On the other hand, I think an important part of the contest, beyond just showing the world that we can do it, is developing a community that now is incredibly, insanely interested in this. And having done that now, we don't have to make the case anymore that it's important or that people are interested or that we should have funding and all of those other things. We would not have been able to do that, I think, without the contest. It created an incredible pool of diverse people who are interested in this problem. And so we're grateful that that happened. It wasn't a guarantee. There were some risks, but the way Nat ran the contest made that happen, and we're grateful that it did.
Definitely. Thank
Well,
you.
let's thank our speaker. So before you go, we do have a few small tokens of thanks. One is a framed copy of the announcement of your talk. Another is our ribbon emblazoned on four sides with the symbol for inductance, which was studied by our founder, Joseph Henry. And the third is a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, in which you'll see the names of the founders, why they founded the society, why they called it the Philosophical Society. And there's a nice discourse in there on how discussion within a scientifically oriented society should take place, which basically says, look, it's no holds barred. You should say what you think, and you should not be intimidated by the consensus. So I recommend that everybody read that. And with that, let me thank you again.
Thank you.
And
Thank you.
before you go, we have a few closing announcements before I adjourn the meeting to the social hour.
Thank you.
Okay, first I'll admit my ignorance. I'm not sure what we're going to do about the next meeting. For various reasons, we may postpone it into July. The meeting after that will be, I won't tell you the number because I don't know for sure, will be on June 14th, and the speaker will be former NASA Administrator Mike Griffin, who is currently the co-CEO of Logic, spelled with a Q. and recently has been lobbying for a kind of scaled back, fast approach to return basically Americans to the moon. And the next meeting will be the last of the 20, probably the last of the 20 lectures of the season. And the speaker will be Ben Schneiderman, and he will be speaking on human-centered AI, ensuring human control while increasing automation. In the fall, the 2,500th meeting will be on 6 September, one way or another. And we will be having a gala celebration of the 2,500th meeting, but also the 150th anniversary, which we didn't celebrate because of COVID and various other logistical issues. It looks like, and don't hold me to this, it looks like this is going to be a presentation on the James Webb Space Telescope from inception to the most recent results, which will have probably 6 people who've been involved with JWST from beginning to now. So hopefully that will come to fruition, and that should be great because, the visuals are stunning, whatever else anybody says. Then we have a speaker on creating languages de novo, of which the most famous that this particular person has created is what? Is Klingon. And actually written an opera in Klingon, if you can believe that. So this should be interesting and fun. And then the next speaker will be Alexandra Gade, who is professor of physics and scientific director of the Facility for Rare Isotope Beams in the Department of Physics and Astronomy at Michigan State University. Her office is located in the cyclotron building, so you can kind of guess what she does. And she'll be speaking on the facility and the structure of nuclei, a magic number violation, and related subjects in physics. We'll post further commitments to the website as soon as we have them, so please check often, www.pswscience.org. Let's thank our volunteers for the hard work of running things. Please return your name badges to the plastic bin in the back of the room. And with that, I will adjourn. Oh, wait, I forgot one thing. I neglected to have the minutes approved as read with the corrections. So if I have a motion by a member to approve the minutes with the noted correction, to have a second. All members in favor? All members opposed? Minutes are accepted, subject to the corrections that we noted, and will be posted to the website in due course. And with that, I will accept a motion to adjourn the 2,496th meeting to the social hour. Thank you, Bob. Do I have a second? Thank you. Have all members in favor? All members opposed? Meeting is adjourned to the social hour.